Alright, 45.1, look at the picture below illustrating the volume and pressure for three separate closed containers, all have the same temperature. If the stopcocks of the three containers are opened, what is the pressure inside the system? Ignore the small volume of the connective capillary tubing. And so we're given a volume and a pressure, a volume and a pressure, and a volume and a pressure. We want to know the total pressure inside of the system when we're done. So we have three gases that are going to, when opened, fill the shape of their container. And so we have initial and final conditions for nitrogen, initial and final conditions for neon. I'm just going to do I and F. And we have initial and final conditions for hydrogen. And we have pressure and volume data that we're going to be interested in, and we're going to assume that the temperature remains constant because it's the same temperature right here. So the initial pressure of the nitrogen gas is 1 atmosphere. The initial volume of the nitrogen gas is 1 liter. The final pressure of the nitrogen gas, we don't know. The final volume is going to be 1 plus 1 plus 0.5, or 2.5 liters. Neon's initial pressure is 1 atmosphere. The final pressure of the neon gas is unknown. The initial volume of the neon is 1 liter, and 1 plus 1 plus 0.5 is 2.5. Hydrogen, the initial pressure is 1 atmosphere. The final pressure is, we don't know. The initial volume is 0.5 liters, and then the final is 1 plus 1 plus 0.5, or 2.5. Now we know that volume and pressure are inversely proportional to one another from the vice-president relationship. And so for each one of these, we have the volume getting larger, which means the pressure's got to go down. And so we'll take our initial pressure right here and multiply by a ratio to make it get smaller. Now our ratio choices are 1 over 2.5 or 2.5 over 1. Which one would make it get smaller? Obviously the smaller number on the top. So 1 over 2.5 here. For this one, same thing. 1 times 1 over 2.5. For this one, 1 times 0.5 over 2.5. Now once we get each one of these partial pressures, we could add those all together. We would get the total pressure into the system. So let's run these through the calculator really quickly. So 1 divided by 2.5, we end up with 0.4. Same thing here, 0.4, because 1 divided by 2.5, 0.5 divided by 2.5, we end up with 0.2. So 0.4 plus 0.2 is 1.0, and that would be in atmospheres of pressure for our total pressure at the end. So notice how we organized each one of the pieces for the bulbs to find out the total pressure at the end. 45.2. Which gas deviates the least from ideal behavior? Well, remember, things that deviate from ideal behavior are ones that are big and clunky because they actually take up space because we ignore the space that they occupy, and things that have attractive forces. And since all of these are nonpolar, we wouldn't have to worry about attractive forces at all. And so the one that would deviate the most from ideal, that would be the largest one, which would be the one with the biggest molar mass. So the one that would deviate the least from ideal behavior would be the smallest one, and the smallest one, of course, would have the smallest molar mass. And so if you add all of these up on the periodic table, N would be 28, neon I believe is just 20 on the periodic table, CH4 is 1 carbon plus 4 hydrogens, so that would end up being 16. C3H8 is obviously much more, and SO2 I think is like 64. So deviating the least would be the CH4 right here because it would be the smallest molar mass. Approximately what volume do 2 moles of H2 gas occupy at STP? So at standard temperature and pressure, we know that 1 mole of any gas occupies 22.4 liters. Now if you forgot that molar volume of the gas, you can always find it right here because at STP 1 mole occupies 22.4. That's only true at standard temperature and pressure. That's only true at 273 Kelvin and 1 atmosphere of pressure, which it tells us we're at. So 2 moles would just be double that, so that'd be 44.8. Number 45.4, some good gas questions here. Here are some choices, and it says, has the average atomic or molecular speed a closest stat at N2? So on average, you move faster if you're small and lighter. On average, you move slower if you're big and clunky. So we want to find one that is closest in molar mass to N2. The closest to molar mass of N2 would be NO right here. If you add up each on the periodic table, first of all, add up nitrogen. That's 28 grams per mole, right? Because nitrogen is 14 plus 14. Carbon dioxide is 44 grams per mole. Hydrogen would be 2 grams per mole. Those aren't too close. Xenon, if you look on here, is 131, so not close at all. And neon is 20. So neon's close, but if you add up NO, nitrogen is 14 plus oxygen is 16, so that would end up being 30. So our closest one would be NO. Number 2 has the smallest density. So density is equal to military police over rapid transit. So you can see density and molar mass are directly proportional to one another. And if we want the smallest density, we want the smallest molar mass. And our molar masses are right up here, and the smallest molar mass would be hydrogen. So letter C, hydrogen, would be our smallest molar mass. Which one would be the largest density? Well, it'd be xenon, right? Because it has the largest molar mass. Number 3 deviates the least from ideal behavior. Well, remember, we want the smallest one, so then we don't have any size, because then if we don't have any size, then you can ignore that size when you're doing the calculations. Remember that ideal behavior of a gas assumes 2 things. We assume that the particles are very small, they have no size, and that they have no attractive force. And so, since they're all nonpolar, we don't have to worry about attractive force, and since they're and you'd never have to worry about that anyway. That wouldn't be the type of the question. You'd get the small size or the large size as the question, because they could ask which would deviate the most from ideal behavior, and that would be xenon, and of course, because it's the largest. The smallest one would be the one that would deviate the least from ideal behavior, and that would be hydrogen. Last one. A flask containing, this is 45.5, flask containing 1 mole, 1.5 mole, and 2.5 mole. The total pressure of the gas in the flask is 1,000 milliliters, which is closest to the partial pressure of O2. So we know that the partial pressures of each of these gases would add up to the total pressure. To be able to find the partial pressure of one of them, find the fraction of molecules that makes up that portion. So by fraction, we need to be part of the whole. So numbers of molecules, of course, we measure in moles. And so we have a total of 1 plus 1.5 plus 2.5. So 5 total moles. And if we're going to do part divided by whole, then our part would be the part that we're interested in, which would be O2. And O2 has 2.5 moles. And so you can see that 2.5 divided by 5 would be 1/2, or 0.5. And so half of the pressure would come from oxygen. And so you'd multiply that times 1,000. And so 1/2 times 1,000 would be 500, which would be letter C right here. You could ask the same question about any of these. So, if it was SO2, it would be 1 mole divided by 0.5. And so therefore, 1/5 of 1,000th of the pressure would come from SO2. And you can do the same thing for O2 as well. More on the next.